So let's look at chapter 4 now. Okay, so if you're going to be a rocket scientist, okay, then you're going to want to, create your rocket fuels that with the correct mixture of reactants, right? So here we see a solid rocket booster, and that solid rocket booster is made up of different chemicals in solid form, and it just burns, But you want to make sure that you have all the correct quantities of each reactant, and they're going to react together to give you the best outcome, or the most thrust in this case. Okay. And then also on the space shuttle, this doesn't show it here, but the space shuttle has a big orange tank right in the middle, and that big orange tank is full of hydrogen and oxygen, liquid hydrogen and liquid oxygen. So it's super cooled into a liquid state, and that's the fuel that they use. And those are going to have to combine in the correct ratios and burn at the correct ratios in order to give the most efficient burn that you could have on that space shuttle. Okay, so it's really important, this idea of stoichiometry. Stoichiometry is how we obtain the correct amounts of reactants and products in a chemical reaction. Okay. So let's look at an example here. Okay. We have methane and we're reacting with oxygen. That methane is going to produce carbon dioxide and water. Those are always, in fact, the products of a combustion reaction with an organic molecule like methane. Organic molecules being carbon-hydrogen molecules. Okay. So carbon-hydrogen molecules reacting with oxygen will give you carbon dioxide and water as their products. All right. So in this reaction, you can see that I have one carbon over here. I have 4 hydrogens. Okay. I have 2 oxygens here, but you'll notice the coefficient. The coefficient is 2 for that O2, which means that I have 2 O2s, which is actually 4 oxygens. 4 oxygen atoms, 2 oxygen molecules. Do you understand the difference between what I said there? 4 oxygen atoms, 2 oxygen molecules. Okay? This is an oxygen molecule. This is an oxygen atom. So the molecule is the whole thing, the O2, and the oxygen atom is one of the oxygens. Okay? Over here I have a carbon dioxide. That gives me 1 carbon, 2 oxygens. Okay, so that's 2 of the oxygens accounted for. And then over here I have 2 water molecules. So here's the other 2 oxygens. And then I have 1, 2, 3, 4 hydrogens. So those 4 hydrogens are accounted for. 2 of the oxygens are right there. The other 2 are right there. That's 4 oxygens. That accounts for the 4 oxygens over here. I have 1 carbon and 4 hydrogens. So everything's the same, and it needs to be. Okay? You don't just lose something in a chemical reaction. You have to account for everything, where they're going and where it is. Okay? So that's why we balance chemical equations. So balancing chemical equations is a process of making sure you have the same amount of things on each side of the reaction. That is called conservation of mass. So there is a conservation of mass. If I react 20 grams of reactants and they all react completely with one another, then on my product side, I would have 20 grams of product. 20 grams of reactants should give me 20 grams of product if everything reacts completely. Okay? So I don't lose a hydrogen from here to here. There's a conservation of it. And that hydrogen has a mass of 1 gram here, and it has a mass of 1 gram over here. So those masses have to be the same. So like with this methane. Okay? So methane carbon is 12 plus the 4 from the hydrogen. That's going to give me 16 grams for methane. O2 is 16 times 2 is 32. Okay, for O2. Carbon dioxide has a mass of 32 plus the 12, which is 44. So carbon dioxide has a mass of 44. Okay, and then water has a mass of 18. Okay, so here we have 16 grams plus 32 times 2, which is 64. Here we have 44 grams and 36 for 2 times 18. These are the masses that are conserved on each side. Okay? So the mass on one side should equal the mass on the other side. 16 plus 64. I have 80 grams of reactants. Okay? And I have 44 plus 36 is 80 grams of products. Right? So there is a conservation of mass. And how do we do that conservation of mass? By following the atoms. That's how we ensure that there is a conservation of mass. Okay? So the law of conservation of mass has to be followed, and balancing chemical equations allows us to do that. All right? Okay. So these are our reactants. Reactants will rearrange to become products. Okay? And when you look at a chemical equation, that's how you always see it. You always see the reactants on the left side and the products on the right side. Okay? And the arrow between showing you which way they go. Now, sometimes you'll see a reversible arrow. And what that means is that reactants can turn into products, but then products can also act as reactants and decompose perhaps, so that's an example, and decompose back into products in a process called equilibrium. And you'll talk mostly about equilibrium next semester. Oh, you're going to talk about it a lot next semester. So, but that's what an equilibrium double-sided arrow means. That the reaction proceeds in both directions until it reaches an equilibrium. Okay? All right. So here we have some methane reacting with oxygen, and it's going to produce carbon dioxide and water. Okay? So I have 1, 2, 3, 4, 5, 6 oxygens, and I have 1, 2, 3 methanes. Okay? So if I have, according to this chemical equation above, that's balanced. If I have 1 methane, it will react with 2 oxygens, right? So if I have 3 methanes, then it should react with how many oxygens? 6, right? So that means that this is stoichiometrically correct. That if I have 1, 2, 3 methane molecules, it will react with 1, 2, 3, 4, 5, 6 oxygen molecules. Well, if I have 6, or let's just say 3 methanes, how many carbon dioxides would I make? According to this chemical reaction and its balance. 3, right? Because 1 methane makes how many carbon dioxides? 1. So 3 methanes would make 3 carbon dioxides. So this is the whole idea behind stoichiometry. It's using those ratios of everything and trying to determine, well, if I have this much of a reactant, how much of a product will I make or produce? Okay? And so that's what we look at. Okay, so here I have 1, 2, 3 carbon dioxides. And I should make 2 waters from 1 methane. If I have 3, then I'll make 6, right? 1, 2, 3, 4, 5, 6. So everything's accounted for. Now, it would be very difficult to carry out a chemical reaction on that level, right? On that level, I'd be hard-pressed to react 3 methanes with 6 oxygens. There's just no way that I could do that. So instead, we use molar quantities, right? And the ratios are still the same. So these coefficients become, they either become atoms or molecules reacting, or you can think of them in moles. So 1 mole of methane will react with 2 moles of oxygen and produce 1 mole of carbon dioxide and 2 moles of water. Okay? And now I go in the laboratory and I can measure out a mole of methane. No problem. I can weigh an entire mole of methane. 16 grams. I can weigh 16 grams. No big deal. I can weigh 64 grams of oxygen. Easily. Okay? I can weigh 44 grams of carbon dioxide and 36 grams of water. So if I produce those, I could determine if I actually produce the amount I meant to produce, like 36 grams of water, by weighing it on a scale after the reaction. And I have this water, and I go weigh it. Does it weigh 36 grams? Was my reaction complete? Okay? So that's what stoichiometry does for us. It creates these relationships between all the reactants and products and allows us to determine, if we start with this amount, how much will we end with? If I have this much of one reactant, how much do I need of the other one? Okay? All right. So let's look at our first example here of balancing this chemical reaction. Okay? Hydrogen and oxygen are mixed and reacted by adding heat to form water as the only product. What is the balanced chemical equation? Question mark. That should be a question mark. Okay. So, what is the balanced chemical equation? So, if I'm going to write this reaction, is that correct? What's wrong with it? I need a 2 where? Hydrogen needs a 2. And somebody said the other one. Oxygen needs a 2. Hydrogen and oxygen don't exist as H and O, right? They exist as H2 and O2. If I'm going to react hydrogen and oxygen, I'm going to react H2 and O2. So if I am going to find the correct balance equation, the first thing I have to do is write the correct equation, right? So if I just write H and O, I will get a different balance, which will be incorrect. But if I write H2 and O2, I will get the correct balanced equation. Okay? All right. So here I have a hydrogen bound to a hydrogen. I have an oxygen bonded to another oxygen. I have an oxygen here bound to 2 hydrogens. Okay? So this is my reaction without any coefficients. And now I want to balance it. So I have 2 hydrogens on one side, right? I have 2 hydrogens on the other side. Balance. I have 2 oxygens, but I only have 1 oxygen. So if I want to balance this, I could approach it in 2 different ways, one of them not correctly and the other one correct. Okay? So here, if I put this as a subscript O there, I just balanced my chemical equation. Okay? So what do you think about that? You don't like it? I changed the compound. So here I was showing you the compound of water, right? That's not water anymore. It's hydrogen peroxide, right? It's hydrogen peroxide. That's not what I want. I don't want hydrogen peroxide. I want water. I did not water plus oxygen might produce hydrogen peroxide, but hydrogen and oxygen reacting don't produce hydrogen peroxide. So I can't do that. I cannot change the subscripts. Why? Because the subscripts identify what it is, what the molecule is. So once I've identified what molecule I'm creating, I can't just manipulate subscripts. So what do I have to do in order to add another oxygen then? I will eventually, but not yet. What do I have to do to get another oxygen over here? What's that? Okay, what does that, yes. What does that represent? What does that mean if I put a 2 in front of it? That's what the numbers will be. But what does it represent? Coefficient of 2 represents 2 moles of water. Right now I have 1 water. So to get another oxygen, I need to add an entire other water. Right? Do you get that? Do I have 2 oxygens now? Now I have 2 oxygens, right? 1, 2. So I can't just change that subscript. The only thing I can do is add more of an entire molecule. That's how I balance things, by adding more of the entire molecule on both sides of the reaction. So now, as was mentioned, I have a coefficient of 2 waters. I have 2 water molecules. Okay, so that gives me 2 oxygens. I can multiply this into here and say, okay, that is 2. Okay, and it gives me 4 hydrogens. 2 oxygens, 4 hydrogens. Now I have a balanced chemical equation. Nope, not yet. Now I need to add another hydrogen to make it balanced. So what do? I can't change that. So I need to add another hydrogen molecule. Okay? I need to add another hydrogen molecule. So it's going to now be 1, 2, 3, 4 hydrogens. Coefficient of 2 in front of the hydrogens. 2H2. O plus O2 produces 2H2O, and everything is the same. I have the same amount of stuff on each side of the reaction, which means there is a conservation of mass. Okay, there is a conservation of mass. 2 oxygens and 4 hydrogens weigh the same as 2 oxygens and 4 hydrogens. Okay, conservation of mass. All right, so balancing chemical reactions is simply a matter of making sure you have the same amount of atoms on both sides by changing only, what do we call this? The coefficient. That is the only thing you can change. You can only change the coefficient. You can't change anything else. Okay? Excellent. Okay, nitrogen and oxygen are mixed and reacted by adding heat to form dinitrogen pentoxide. Oops, yeah. O5. Okay, is this my equation? What's wrong with it, or what do I need to do now to it? Okay, that would be so easy. But we're missing one step. That would give me a balanced chemical equation. Yeah, is this an N? What should it be? N2. Nitrogen also exists as a diatomic molecule. Okay, now I can balance it. Oh, man. Okay, O2, right? There we go. Now I have all my molecules as they should be. So, nitrogens are balanced. So I don't need a coefficient for that one right now. What about my oxygens? Oh, that's a very good way to do it. Okay, I'm going to show you a couple ways. First, I'll show you how she was saying it. So, if I just flip those, right? Then I'll have a 5 here, that's 10 oxygens. A 2 here, that's 10 oxygens. Now my oxygens are balanced, right? The only thing that's not balanced now is the nitrogens. So, but no big deal. I put a 2 here. Now I have a balanced chemical equation. Okay? Everything's the same on both sides. That's one way to approach it. Okay? Another way you could approach it. There is a coefficient that I can put in front of oxygen right here to make this balanced. What is it? If I want 5 oxygens, what number times 2 is 5? 2.5, right? 2.5. So 2.5 times 2 is 5. 2, 5, 2, 5. Is it balanced? Yes. It's balanced. You don't like that, do you? Well, I'm getting all kinds of dirty looks. Okay, so this is a balanced chemical equation. The only problem is that you can't really have half of an oxygen. You can't have 2.5 oxygens, right? But you can use this as a tool. This is a tool to find what the balance is. And once you find the balance, all you have to do is multiply every coefficient by 2 to get rid of the fraction. 2, 5, 2. Is that the same balance equation we had earlier? Yeah, it is. Okay? So that's 2 approaches. Because the switching thing doesn't always work. Okay? This will work when you have to find, the fraction will work when you have to find a balance. And then you just multiply everything by 2 to get rid of that fraction. Okay? And then you will still have your balanced chemical equation. As long as you multiply every coefficient by the same factor, then it will maintain the balance. Okay? And because it's a half, to get rid of the half, I multiply by 2. Right? And really, that's the only one that you're ever going to have to deal with. You don't really deal with quarters. I mean, I've done it before where I've been like, okay, I'll take a quarter there, and that gives me a balance, and then I'll multiply by 4. Right? But you won't see anything like that, I don't think. Okay? So, that's what we're going to do. Okay? So that's 2 approaches there. All right. You guys try it. Try this one. Try and balance this chemical equation. Okay? Okay, and I'm going to give you some advice. Don't balance the oxygens until the very, very, very last. Okay? Because if you do that, then you can put a coefficient in front of oxygen so that it can be any number you want. You could make that oxygen 1. What number in front of that oxygen would be 1? 0.5. 0.5 times 2 is 1, right? What if I wanted it to be 3 oxygens? 1.5. So if you balance the carbons and the hydrogens and then leave oxygen to the very end, you can make that oxygen any number at all to make it balance. So because it's all by itself, it won't affect any other thing. So if I change the coefficient of the oxygen, it won't affect any other thing. So leave it to the very end, and you can balance it by putting a number in front of it that will make it the correct number you want. Okay? I saw some pretty creative balancing out there, by the way. Multiply everything by 2. Okay, so let me give you a little more advice.